Good morning, students. Welcome to video lecturing class for the subject Dynamics of Machines. So today we'll start with the fifth module, and that will take up the forced vibration section. So basically, the forced vibration of a single degree of freedom system occurs when work is being done on the system while the vibration occurs. That is, a mechanical or structural system is often subjected to external forces. Those external forces may be harmonic or non-harmonic, periodic or non-periodic, but having a defined form or random form. So the response of a system to harmonic excitation is called harmonic response. Similarly, the response of a system to a suddenly applied non-periodic excitation is called as transient response. Similarly, the sources of these responses are maybe anything, but the most typical examples of random forcing functions are, you can take the earthquake excitations and the acoustic excitations. It is all come under the random forcing functions. Then the external excitation to a system can be easily detected, and the another excitation is the internal, and this occurs due to unbalance or defects in the system itself. Okay, so the unbalance in the system occurs due to, first one is the rotating or rotating and reciprocating parts. Second one is the magnetic effects. Third one is due to loose or defective mating part, and fourth one may be due to the thermal effects, and fifth one is due to the bearing or journal defects, and the next one is due to the variation in the turning moment of the engine, or there are many reasons. So basically this force vibration of single degree of system occurs when the work is being done on the system while the vibration occurs. Okay, so whenever your system is running, okay, so that time if the vibration is occurring, that vibration we can call it as forced vibration. Now moving further, the forced vibration of undamped single degree of freedom system. So let us consider an undamped single degree of freedom spring mass system. So initially it is excited by a sinusoidal forcing function, that is F omega equal to F naught sine omega t, that is F omega equal to F naught sine omega t, or F naught cos omega t is shown in this figure. So here the F naught is amplitude of force and omega is circular frequency of the forcing function. So now the external forces acting on the systems you can see from this free body diagram. The first one is spring force, that is Kx, which is acting in upward direction because the displacement is occurring in downward direction. And the second one is F naught sine omega t, which is the applied force. It is acting in the downward direction. So now from the Newton's second law of motion, we know that the acceleration force or acceleration torque or acceleration resistance should be equal to the restoring force. So that is mx double dot is going to be our acceleration force, should be equal to summation of all the forces including applied and reaction forces. So from this free body diagram you can write it as mx double dot equal to minus kx plus f naught sine omega t. So here for this kx I have taken the negative sign because it is acting in upward direction, and f naught sine omega t is acting in downward direction. And it is not like always you have to take upward forces as negative and downward forces as positive. It is not like that. Actually you have to observe the direction of the displacement. So in this case the displacement is occurring in the downward direction. Meanwhile your acceleration force is also acting in downward direction. So in such cases, you have to take the forces which are acting in the downward direction as a positive and upward direction as negative. Remember this very carefully while writing the differential equation for any system. Okay, so we have to take the positive sign for the forces which are acting in the direction of the displacement of the body as a positive, and which are acting in the opposite direction. For those forces, you can take the sign as the negative sign. So if I simplify this, x double dot plus k by m into x equal to, so here I have taken m as the common, or I have divided the whole equation by m, which is equal to f naught by m into sine of omega t. So here this equation is a linear non-homogeneous and the second order differential equation. So the solution of this kind of equation consists two parts. One is complementary function and the other is particular integral. So therefore we can write the solution as x equal to xc plus p, where this xc is complementary function and xp is particular integral. So the complementary function is obtained by differentiating the equation, that is mx double dot plus kx equal to 0. So therefore we can write the solution for this equation directly as xc equal to x into cos of omega nt minus pi. And how to write these general solution already we have discussed in the previous chapter. Okay, so for this kind of differential equation directly we can write the solution in this form. So now let the particular integral solution in the form of xp equal to, let's assume that there is a sin omega t plus b cos omega t, where these a and b are the constants. So if you differentiate this one, x dot p equal to a omega cos omega t minus b omega sin omega t. Similarly, if you differentiate again this one, you will get minus a omega square into sin omega t minus b omega square into cos of omega t. So now if you substitute these x double dot p and xt and x dot p in equation number 1, that is differential equation, you will get this. That is here the equation number 1 is x double dot plus k by m into x dot equal to f naught by m into sine of omega t. If you substitute these values in that equation, you will get this equation. Once to simplify this equation, that is bring all the sine omega corresponding sine omega t to one side and cos omega t to another side, just separate these terms. Okay, now I can write here one more term, that 0 into cos omega t. This is just for the simplification purpose. If it is multiplied by 0 means it is 0 only. So now if you equating the coefficient of the sin omega t and cos omega t on both the side of the equation. So now here I am having minus a omega square and k by m into a for the sin omega t on this side, and on this side is f naught by m. So I am equating these two here. Similarly, for the cos omega t I am getting it as minus b omega square plus k by m into b equal to 0. Okay. Then from equation a, that is from this equation, I can take a as the common term. So I can rewrite it as k by m minus omega square equal to f naught by m. So from this I can get the a value as f naught into m, f naught by m divided by k by m minus omega square. So here it is f naught by m. So, okay. Now from equation b, it is b into k by m minus omega square equal to 0. Since this term cannot be 0, so I can directly write b as 0, because this term contains mass, spring stiffness and omega, so we cannot take these values as 0. So directly I can say that this constant can be 0. Now if you substitute these a and b in equation number 2, that is in this equation, that is the xp equation, will get xp as f naught by m divided by k by m minus omega square into sin omega t is the a value, minus b is 0, is equal to f naught by m into sin omega t divided by k by m minus omega square. So now here we know that omega n is the root of k by m, so omega n square will be omega n square will be k by m. So in place of k by m, I will substitute it as omega n square. So now from this equation, this is f naught by into sin omega t divided by m into omega n square. I am taking omega n square as common here. I will get it as 1 minus omega by omega n whole square, which is equal to f naught into sin omega t divided by m into k by m, that is omega n square value is k by m, 1 minus omega by omega n square. Or I can rewrite it as xp equal to f naught into sin omega t divided by k into 1 minus omega by omega n square. So here in place of omega n square, again I resubstitute it as k by m. So m and m will get cancelled here. I am left with only k here. So therefore the complete solution of that differential equation number 1 can be written as x equal to xc plus xp. So xc value is x into cos of omega n t minus pi, plus xp value is f naught into sin omega t divided by k into 1 minus omega by omega n square. So now in this equation 3 shows that the motion of mass is equal to the sum of the free vibration and forced vibration response. This is for free and this is for forced vibration. And the ratio which is written here omega by omega n is called as frequency ratio. So if the free vibrations of a complementary solution represented by the first term, that is xc, if we neglect that, then the displacement of the undamped force vibration can be written as x equal to, just in this equation you have to ignore this term, just write xp apart, f naught into sin omega t divided by k into 1 minus omega by omega n square. So now when sin omega t equal to 1, the displacement we can take it as maximum. So x max will be f naught by k divided by 1 minus omega by omega n square. Okay, so this is the simple derivation for the simple spring mass system. Then moving further, the forced vibration of damped single degree of freedom system. So here the one more element has come, that is the damper now. So previously it was just a spring mass, now it is spring mass damper system. So for this, let us consider spring mass damper system having the viscous damping excited by sinusoidal forcing function, that is f of t as f naught into sin omega t, which is shown in this figure, and this is the free body diagram for that system, given system. Okay, so here this line shows the level of equilibrium under the weight of the body. So let the mass m is displaced from the static equilibrium position through a distance x in the downward direction. If you are giving the initial displacement to that mass, definitely on that body some external forces will act. Okay, so those external forces are, that is the forces which are acting on the system are, first one is external applied force, which is a harmonic function. It is f naught into sin of omega t, which is acting in downward direction. Spring force kx, which is acting in upward direction. Damping force cx dot, which is acting in upward direction. Now for the dynamic equilibrium, the sum of all inertial and external forces in any direction should be equal to 0. Or you can directly apply the Newton's law of motion, that is acceleration force will be equal to restoring force here. So acceleration force is mx double dot, which is equal to restoring forces are f naught into sin omega t. It is a applied force, external force, which is acting in downward direction, and the displacement of the body is also in downward direction. Hence I am taking this term with a positive sign. And this damping force and spring force are acting in upward direction, Upward means in this case they are acting in opposite direction of the displacement, because your displacement of the body is occurring in downward direction. So I am taking these two terms with the negative sign. So if you simplify this to the standard format, that is mx double dot plus cx dot plus kx equal to f naught into sine of omega t. So we will call this equation as first equation. So now to analyze this, there are two methods. One is we can go with this differential equation method, and another is graphical method. So first we'll try to go through the differential equation method. So in the above equation, that is equation number 1, if you see that it is also a linear, non-homogeneous and second order differential equation. So the solution of this kind of equation also consists of two parts. One is complementary function and other is particular integral function. So directly we can write the solution for equation number 1 as x equal to xc plus xp, where this xc can be obtained from that differential equation, that is mx double dot plus ax dot plus k equal to 0. For this kind of differential equation, directly we can write the general solution as x into e raised to minus zeta into omega nt into sine of omega dt plus pi. And for that second part, that is particular integral part, xp as xp equal to a sine omega t plus b cos omega t. So now from this equation, first we need to identify the value of a and b. Substituting this equation in equation number 1, that is in place of x dot and x double dot and x, will get a as minus b into k minus m omega square divided by c omega. Now if you substitute this a in the same equation, we will get b as minus f naught into c omega divided by k minus m omega square whole square plus c square into omega square. Now if you substitute this a and b in equation number 2, okay, that is xp equation, we'll get f naught into k minus m omega square divided by 2 bracket, again a bracket, k minus m into omega square whole square plus c square into omega square into sine of omega t. This is the a value and this is the b value. Now if you simplify this equation, okay, so we'll get xp as f naught divided by k minus m omega square into square minus c square into omega square into x cos pi into sine of omega t minus x sine pi into cos of omega t. So here after simplification we'll get the value of xp here, that is in this equation where this x cos pi is k minus m omega square and this x sin pi is c into omega. So here I missed one term here, you have to write that c omega is there, okay, because that is the value of your b. Yes, b is f naught into c omega. So here I have forgotten to write c. Okay, so it is c omega is equal to, you have to substitute as x into sine pi. That is in this equation. Okay, here we have written that. So now let us consider these two terms which are substituted. So if you square and add these two, that is x square into cos square pi plus x square into sin square pi equal to square of this plus square of this, we'll get the value of x, because sin square theta plus cos square theta will be 1. So x will be k root of k minus m omega square whole square plus c into omega whole square, and you can write the angle pi as tan inverse of c omega divided by k minus m omega square. So now this equation 3 can be rewritten as xp as f naught divided by k minus m into omega square whole square plus c square into omega square into x into sine of omega t minus pi. Okay, so that is f naught into sine of omega t minus pi divided by root of k minus m into omega square whole square plus c square into omega square. Now the complete solution of that equation is x equal to xc plus xp. So where this xc value is x into e raised to minus zeta omega nt into sine of omega dt plus phi, and xp already are derived. So if you substitute those two, and if I ignore this xc term because for the undamped factor, so I can rewrite the x value as f naught into sine of omega t minus phi divided by this term. So this equation shows that the motion is the simple harmonic motion where the circular frequency is omega and the amplitude is f naught divided by root of k minus m omega square whole square plus c square into omega square is the amplitude. And maximum amplitude of vibration, if you ignore this sine omega t minus pi as 1, if you take that value as 1, the x max will be f naught divided by this term. Now if you divide the numerator and denominator by k on the right hand side of the equation number 4, you can write the equation as f naught by k. If you are dividing, if you go into the root, under the root, it will be k square. Okay. So here I am dividing the numerator and denominator by k here. Now the numerator as it is f naught by k, and in this I am taking k as the common term. Okay, so I am left with 1 minus m by k omega square whole square plus c by k into omega whole square. Or I can rewrite this equation as x naught divided by 1 minus omega square as it is. This is m by k. I can rewrite it as k by m. So k by m is nothing but omega n. So it is omega n square plus, and here I can replace this term by 2m into zeta omega n into omega divided by 2k whole square. That is, for x naught is for the zero frequency, deflection is f by k, and omega n is root of k by m, and in place of c, if I substitute it as 2 zeta into m into omega n, which you already learnt in the previous module. That is, damping coefficient is given by 2m into 2 zeta into m into omega n. I am substituting that here. Okay. Then I can write the equation as x max as x naught divided by root of 1 minus omega by omega n square whole square. So here this x naught is nothing but zero frequency deflection, which is equal to f by k. Remember this, plus 2 zeta into omega by omega n whole square. Okay. So here I am having 1 omega n and I am having m by k. So m by k is nothing but 1 divided by omega n square. So 1 omega n with this omega n will get cancelled here. That is why I am left with only 1 omega n. Okay. Then if I resubstitute this r as omega by omega n, that is frequency ratio, I can rewrite the equation as x max as x naught divided by root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so remember this in the form of r only, it will be easy to remember the equation. So these equations you have to remember to solve the problems. Okay. Then the second method is the graphical method, we are going to discuss now. So in the graphical method, let us assume that the displacement of the vibrating mass is shown in the figure under the action of applied SHM is also a simple harmonic and lags by an amount of phi, so that it can be represented by the equations like x equal to a sine omega t minus pi, x dot, x double dot, spring force is kx. In place of x, I have to substitute this. Damping force is cx dot. In place of x dot, substituting this equation. And inertia force is mx double dot. So in place of x double dot, I have to substitute this one. So here I am adding the 90-degree angle just to convert that cos angle to the sine angle. Okay. Now in this, from the triangle ORS, Okay, from this triangle I can write this OR as root of OS square plus SR square. Again, where this OS is OP minus PS. Okay, where this PS is KX, sorry, OP is KX, and this PS is M into omega square into X. So substituting those values, I will get F naught as F naught equal to X into root of K minus M omega square whole square plus C into omega whole square. So before that, let us try to understand how to construct this graphical method. So here from those given equations, we can see that the damping force leads the spring force by 90 degree and inertia force leads the damping force by 90 degree. That is here. Sorry. If you see here, the difference like angles are 90 degree each other. Okay, damping force leads the spring force by 90 degree and this inertia force leads the damping force by 90 degree, which is shown in this figure. Okay. Now in this vector representation, this OA represents the maximum spring force. It is drawn to some suitable scale at an inclination of omega t minus phi to the horizontal in opposite direction of the displacement, and vector OB represents the maximum damping force. That is, this O to B represents maximum damping force, and it is drawn to the same scale at 90 degree to vector OA because the difference between their angles is 90 degree there. Okay. Similarly, OC is represented by M omega square into X, and it is drawn the same scale at 180 degree to this OA. 180 degree to this OA. Okay. The projected length of the vectors on the vertical axis represents the instantaneous values of the forces at a time t. So here that OD represents the value of applied force, that is F naught sine omega t at the same instant. This range is F naught sine omega t. So now the force vector OD must be the vector sum of OA, OB and OC, or the force F naught must be the vector sum of Kx, C omega x and M omega square into X, which is shown in this figure. Okay. So now moving further, we can get the X as F naught divided by root of K minus M omega square whole square plus C into omega whole square. So where X is the amplitude. So from the triangle ORS, we can write the tan pi as this equation RS by OS, where RS is C omega X divided by Kx minus M omega square into X. Okay. So when damping is negligible, so from equation 5 we can write X max as X naught divided by 1 minus omega by omega n whole square, which can be written as F naught by K divided by 1 minus omega by omega n square. At resonance, when omega equal to omega n, that time directly we can write X max as X naught divided by 2 zeta or F naught by K, where this is the zero frequency displacement is given by F naught by K divided by 2 zeta. These are the two methods. Now moving further, the next one is the magnification factor. Basically, the transient vibrations die out within a matter of short time, leaving only the steady state vibrations in all particular systems. So the study of the behavior of steady state vibrations are very important here, because it gives you the behavior of the system until the last vibrations. Okay. So now the basic definition of this magnification factor is the ratio of amplitude of steady state response to the static response under the action of force F naught is called magnification factor. It is denoted by F, and it is given by X max divided by X naught, which is equal to 1 divided by square root of 1 minus omega by omega n square whole square plus 2 zeta to omega by omega n whole square it is, or you can rewrite it as 1 divided by root of 1 minus r square whole square plus 2 zeta r whole square, like that. In this omega by omega n, you can replace it by r here. Now this, moving further, graph shows the plot of magnification factor versus omega by omega n for the various values of zeta, that is damping factor. So here the curve shows that damping increases or zeta increases, the value of magnification factor decreases. As the zeta value increases, okay, so the magnification factor will decreases, or if the zeta increases, the magnification factor will decreases. Okay. So when there is no damping, that is when zeta equal to 0, it reaches the infinity at omega by omega n equal to 1. That is, the omega by omega n equal to 1, at that point it will reach to the infinity when zeta is 0. Okay. So here you can see that the phase angle phi varies from 0 to 0 at the lower frequency to 180 degree at the higher frequency, that is from the second graph. So at if it is 90 degree at resonance, that is when omega by omega n equal to 1 and is independent of damping, the phase angle phi is the measure of phase difference required to attain the maximum values of f0 and xmax. So here they do not attain the maximum values at the same time. Okay. So now in the same case, that is for the magnification factor, for the smaller values of omega by omega n, that is when omega by omega n is less than 1, both inertia and damping forces are small, so which results in the smaller phase angle. Therefore the magnitude of impressed force is then nearly equal to the spring force. Okay. So similarly, if the omega by omega n equal to 1, the phase angle will be 90 degree. If the omega by omega n equal to is greater than 1, then the inertia force increases very rapidly and its magnitude is very large. Okay. And the damping and spring forces are small in magnitude at that time, and the phase angle is very close to 180 degree, that is here. Okay. So we'll conclude the today's discussion here itself. So if you have any doubt, you can leave the comment in the comment box. Thank you.